Hi guys, I am Nitin, and in this video I'm going to talk about image ranking models. And I'm not only going to talk about ranking models, but I'm also going to share you the code which I use to train such a model. Now, it is very interesting to know that various kind of models is available right now, which are awesome. So, for example, there is Clip, which allows you to compute image embeddings and then find similar images using the cosine distance between these embeddings. And apart from Clip, there has been also new advancements. So there are also new models available. For example, Meta has their own ImageBind model, and then I have been using DreamSim, which is also one of the amazing models for image ranking. And I recently tested out the Unicom VIT extractor from Quadrant, which is managed by them. So now what is the problem with these models? These are very good at zero shot image ranking, but none of them will be as accurate as per your own data. So if you don't have a lot of data to train your model or begin with, then it's fine. You can use any of these models to just get the task done, or for at least initial phases. But when you move on forward and if you have enough data and you want absolute maximum accuracy, you need to pivot towards training your own models. And I have been trying to do it for years now, and I have various videos on my channel related to this particular topic as well. And today I'm going to tell you about another amazing open source project which is called Open Metric Learning. Initially it was hard to get this up and running, but over the years, all the tutorials which I have followed and all the experience which I have gained, I am able to run this. So it's my duty to put it all together into a containerized environment so that you guys can run it without any hassle. I will talk about the code. I have the notebooks prepared, so I will just go through it and talk about every part so that it is easier for you to follow. So the dataset which I'm going to use into this code is called 200 bird species classification. This is a very good dataset and quite old as well. And in my previous videos, I have used the same dataset, so it makes sense to use the same one. So what this dataset looks like is you will have uh, images of birds of different breeds. Mostly there are 200 bird species, and the goal is to identify each and every species given an input image. Now if you see in the code example, over the years numerous examples are there where people have tried to do it and with a different method. The problem is mostly people will target to train a classification model. So classification model will have your exact number of classes defined, and it only classifies between these classes. So apart from it, the differences between image ranking model is it gives some embedding vector to a image which can be stored and then ranked into some vector database based on cosine similarity metric, and you can find the top k matching. So it's not only classifying your images, but it's also giving a way to rank your images such that you can put all the similar images together and then sort them by their similarity. So let's start with the code. And to get this data, what you have to do it, you will have to first of all visit this URL for the dataset, and you need to be logged in to be able to see this download button. Once there, just click on this download, and let me just show you. Download as zip. Okay, and it will show you in your download history. You just have to cancel this and then copy the download URL and paste here. That's all. With this, you will be able to download it directly in your Jupyter Lab environment. One thing I forgot to tell you about the container setup. So once you clone this repository, you will have this directory and these many files. And the important one here is docker compose.yaml file. Let me just quickly cat its content. So there are two microservices which you will see here. One is your image embedding quadrant microservice, which is a vector database so that we can store our images there and then find similar images without overburdening on our memory and do it efficiently. Another one is your this Jupyter Live environment, which will have all the dependencies set up as well as GPU mounted so that you can just run it and then start training your own model. So once you run this wget command to download the dataset, you can run this additional cell which will extract the content as well as remove any unnecessary files. And after that you will have this, because these images are stored into a single directory, we want training and validation set. So I have some import student here, and the important one here is resize and pad, which is a custom function I have written so that we can resize the images to 224 by 224 dimension. And if the image ratio does not matches, it will add the black padding around the images to make it a square image without losing the structural features of the image. So here in the for loop, what I'm doing is I am equally dividing the image into train and val set. So you will have equal number of images in training as well as validation sets. And after that, to use this model, to use this open metric learning repository, you need to prepare a dataset in a format which can be read by the data loader. And to do that, the simple way is to generate a CSV file. So I've written this function where you point it to the root directory of the folder where you have your images for the training and validation sets, and it will just iterate over those files and generate a CSV. There is two data frames here. One is for training, one is for validation. And finally, what it does is it will just concatenate these two data frames and then save it as a single CSV file. And with this, your data set should be prepared. Let me show you how it looks like. So once you go there, I have some additional files for testing, but basically we'll have this df.csv file, which contains the label and image path as well as the split they belong to. And you have this training and validation directories in which you will have one directory per class, and in each directory you will have a number of images for that particular class. If you see these images, since the background is black, it's not properly visible, but you should be able to see the black borders around the image, which makes it a square image. So now let's move on to and talk about the training. So to train the model, you need to modify this train.yaml file as per your dataset. Since we are into a Docker container, so the path should be based on the container. And if I open a terminal here, you will see our current working directory is /notebooks, which means if you have downloaded your dataset here in the downloads directory, you will have to put it here as /notebook/downloads and then the path. Additionally, if you are confused about what path to use, you can come up here and just click on the copy path, and you will see it is something like this. You just have to put a slash here and that /notebooks, and that will become your absolute path to the directory. So for now, this is my dataset root path, and inside that path I have a df.csv file which I am going to use for training. And I am going to store the train model into current directory as weights directory name. And couple of things you need to take care of here is the batch size. So based on your available GPU VRAM, you will have to modify these two. So this is a data set sampler, and you don't have to pass a batch size because it depends on how many labels of different classes, how many instances of that class we are using, and that constructs your number of images in a batch. So here you just need to multiply these two values and that will become your batch size. So just to make sure that whatever batch size you want to use, uh, divide them into two parts. You can keep the n instances smaller as compared to n labels, but multiply these two and you will get the batch size for training. And for validation, you can define a particular batch size. So I have defined 64 here, and that should work for you. So after this, once you have modified your training.yaml file, there are some additional ones, but I won't recommend modifying those. And there's also a weights and biases logger, which I have disabled for now, but you can enable it and then put your own API key, so you will be able to see those nice training graphs. So to train the model, I just simply need to run python train.py, and that should give me the weights. I have already trained the model, so I'm not going to run the training, but you get the idea how it works. So let's move on to the inference. Inference is a notebook which actually I've not completed. So basically, what it allows you to do is it allows you to load the weight files and compute embeddings. So it could be particularly handy for you if you want to just test out how your model performs. If I run this right now, you will see that it is going to load three images. Two of the images, the first and second image, are of from the same class, and the third image is from a different class. And the goal here is to check how well the model is able to separate between images of a similar class or same class and images of a different class. And you can see the cosine similarity. So when the images were from a same class, it gets a score of up to 80%, and when the image were from a different class, it only gets like 0.006, that is like 6% similarity only between the images. So that's how you compute the embeddings. And finally, I also have this interesting evaluation notebook which allows you to use the quadrant vector database to index training images, and then use the val images to come to predict label for those images, and then figure out the accuracy at which your model is performing. Basically, it means how well your model is able to identify the image. So again, here I have done the same thing, which is testing cosine similarity between similar and non-similar images. And interesting thing here, so I have to define a quadrant client where I would be putting my data, and then I'm listing out images from train set and well set. And here in this cell, what I'm doing is I am making sure that if there is a collection, it should be deleted, so that we start with a fresh index. And I'm using a batch size of 128, meaning I'm loading 128 images to load, and then compute embedding, and then put it into the index. And similarly, I have a search data function which takes in a batch of images and predicts label for those batches. And finally, what I do is I iterate on all of the val images and compute a label from the stored index which is built on training image, and using that information to compute accuracy. And here you can see I get an accuracy of 86%, which have been not achieved before on this channel. So previously, when I tried to train these kind of models, I only achieved like 50 to 60% accuracy, but 86 is a huge win. And even if you compare this score with available models like Clip, you will see that Clip will go up to like 50%, and DreamSim will go up to like 76% only. So no models which is generalized on all kind of images will achieve up to 86% score in my testing. So this is about open metric learning. You can prepare your own data set and then train your own model. I know this video is short and I have not run this courses because I've already tested it, and I wanted to keep this short and small, but you will get the link to this repository in the description, and you can train your own model. And if you have any queries, you can just reach out to me or put in a comment, and I should be able to reply to that. So that's all for this video. I hope you guys enjoyed it, and please do comment, interact with the video, and that will help me to make more such videos in the future.